Hello, I'm Greg Westwater. I'm a member of the NAFEMS Simulation Governance and Management Working Group, and I'm joined again here today by Bill Oberkampf, also a member of that same working group. And today we're going to be talking about model predictive capability. So, Bill, I wanted to start out, what's meant by that term, model predictive capability? What's the purpose of that term?
Well, it's a relatively new term over the last decade or so, and it's a general term that has the context of what do we believe is the capability of simulation software to predict uh, future responses of systems, performance, reliability, safety. And so it's a relatively general term. And it's a useful term because the more technical issue is what we call predictive uncertainty, which we can get into here shortly. But predictive capability is the stress on what do we believe the simulation capability is, as opposed to looking backward in terms of validation or calibration. So it has that emphasis, which I think is good.
Okay, so I've got a few follow-up questions there from your response, but let's start a little bit. You mentioned right there at the end model validation and that predictive capability is distinct from model validation. Do you want to highlight that just a little bit more?
Yeah, we talked about that in an earlier video, and specifically model validation and calibration. And the best way to think about those are looking backward in time. Specifically, model validation is an assessment, an accuracy assessment activity. How well do we agree or disagree with experimental measurements of, it can be a complete system, a subsystem, component, makes no difference. And as we talked about in the previous video, model calibration is a model improvement activity, and implying we have experimental data to update, let's say, input parameters or parameters. There are some parameters that we talked about that cannot be measured outside or independently from the model itself. And we talked about, for example, stiffness and damping in a vibrating structure. You have to measure those with a model. So they're done in solving the inverse problem. Whereas what we're talking about here is in predictive capability, what do we believe the capability is in terms of predicting future events or future responses to a system that we have never exposed the system to that, and maybe it's an accident environment that we hope the system is never exposed to, but what is the safety of the system if it were exposed to that?
Okay, so I know in the past we talked about the idea of a validation domain, the range of conditions, sizes, whatever that we've validated that model to. Um, is model predictive capability the idea of how confident are we once we move outside of that validation domain to potentially extrapolating to new conditions?
Absolutely, and that's why this new term, predictive capability, as I said, it's looking forward. And so if you think about what we talk about in the model validation, or closely related to calibration, but they're different. Those are in assessing model accuracy or improving model accuracy where we have experimental data. Maybe you could say experience with existing operating systems or the system in normal operating environments. But what we're talking about here, and where we don't realize it, but we almost always apply our models or simulation capability to cases, or I'd call it excitations, where we have no data. And we don't usually think of it that way, and it's kind of a scary thought, but that's actually what we're doing. Where we have data is normally what we call in the model validation domain, which we may then turn around and use in calibration. but we use our models. They are so capable that based on physics principles and calibration, we use them where we have never used them exactly before. So that's the distinction that we're talking about.
Okay. So what are then some of the contributors to uncertainty when we move into that prediction?
Okay. And that's exactly the right question, Greg. Let's talk about what are the from the very beginning of code verification is an activity that we've made a video on. And that's an assessment, that's a testing of software and the algorithms. And code verification uncertainty, most people call it errors because it's a different kind of error. It's analogous in experiments to what we call a bias error. And we try to remove bias errors in experimental measurements. But in code verification, we have to build on that foundation of very solid testing of the software. But in terms of what you're asking about, what are the uncertainties in prediction? The first one is on the numerical side. It is numerical solution error. That is error in numerically solving. The differential equations can be partial differential equations, integral equations, makes no difference. So how can we estimate what the uncertainty is due to the numerical part? It has nothing to do with physics. And then on the physics side, there are different kinds of uncertainty. There's uncertainty in the input data to the model. And input data, we can solve a deterministic problem, that's fine. But if we recognize that there are uncertainties in the input data, it can be uncertainties in the system itself or in the environment that is exposed to, like excitation of a structure or flow rate. Okay, those are all system. And then there's another kind of uncertainty, which is actually the most troublesome, which is called model form uncertainty. It is uncertainty, or you could say weaknesses, in the model form structure of the model itself. So those are the uncertainties that contribute to what we call predictive capability.
Okay. And as you mentioned, I think we've talked about each of those in some of our prior videos. So understanding that those risks are there, what do we do to mitigate those risks when we're extrapolating to new conditions?
Okay. The first thing that should be done is to try to quantify those uncertainties. That's the first step, because uncertainty and risk, they're related, but they're different kinds of things. Uncertainty doesn't directly address risk. For example, you can have a large uncertainty, but if it is an uncertainty in something that really doesn't make a whole lot of difference, it may not pose a risk to your organization or to use of the simulation in decision making. So the first step is to try to quantify the uncertainty in those contributors. For example, in numerical solution uncertainty, the most common way that is done is people look at, let's say, different mesh generation, and you look at the sensitivity to different mesh resolutions. Well, that's a qualitative step. You could call it a sensitivity analysis. But if you have a numerical error estimator, you can actually quantify it, okay? And then on the other side of what is the uncertainty in what's called model form uncertainty or model structural uncertainty, that one is actually very difficult to quantify. But people know about these things. And let me give you two examples. In fluid mechanics, if you say, what is the uncertainty due to various turbulence models or combustion models? Okay, people know those things exist. So if you were to do a simulation using different turbulence models or different combustion models, that is actually a model form uncertainty. And you're getting a feel for how much does it affect the simulation result. And when you put all of those uncertainties together, then the decision maker or the designer asks the question, are these uncertainties acceptable for the decisions or the design I want to make? Then that moves over into the risk side. So maybe that helps give you an overview, Greg.
Yeah, I think it's helpful. It reminds me once of a manager that I had who he says, I get upset every time I hear somebody say, yeah, I feel comfortable with this decision. It says I want that data to be based on, or that decision to be based on data, and
Mhm.
I think that's part of what you're talking about there is moving from a qualitative assessment to trying to quantify that so that you can make a data based decision rather than an emotional or a qualitative type decision.
Yeah, and I think the manager you were talking about, even though he didn't use the terms that we're using now, I think he understood what is your estimated uncertainty in your simulation result, because they can come from different places, and how much uncertainty a manager is. It's called risk tolerance. How much uncertainty can they deal with? Well, that depends on every kind of application. For example, if it's a safety matter, maybe you will never do an experiment on a particular failure mode of your system, but you have to be very confident that the system is safe, even if in a failure situation.
Yeah. So to conclude here, then, how do we communicate the predictive ability of a model? What is it that we need to put into a report or tell our managers or the decision makers?
Okay. I think the most important element is what do we estimate as quantitatively? This is the I'd call it the gold standard. What is the estimation of the total uncertainty that we estimate for the various conditions that you were asking a result for a design or for performance, reliability, or safety? Now, many times we don't, that takes a good bit of what's called non-deterministic simulation, but at least give the manager an idea what are the sensitivities to the various assumptions. For example, I mentioned the turbulence models, but in solid mechanics, there are other kinds of things like what is the uncertainty if we move into the plastic deformation or the large elastic deformation range, or we are talking about structural dynamics. What are the sensitivities to this? And that's a qualitative answer, but it gives the decision maker an idea what are the sensitivities. And for example, if they see very large sensitivity, they may say, well, we need to quantify this a lot better. Or in the extreme, we may say, we cannot allow our system to operate in this environment because the uncertainties become too large because we can't predict it. Or he may say, we need to do an experiment to see how well our system performs in that environment. So those are some ways that managers should think about how do they use simulation in decision making.
Thank you, and I think that really resonates with me. I've seen in the last couple of months the tremendous power of persuasion our reports can
Mhm.
have. And I think it's really incumbent upon us to try and be clear about, I'm making this assumption, or we're sensitive to something that we haven't fully defined yet.
Mhm.
And so I appreciate those remarks. Those resonate well with me. So
Okay.
thank you for your time today, Bill, and we will look forward to next time.
Yes. Thank you, Greg.